begin as soon as we get lights, cameras, and action. We'll go and get started. Don't know of many announcements. Do know this one. I think I've told you about the SACS Accreditation Committee, being on campus, that kind of stuff. From what I heard, there was a meeting this morning. I know there was a meeting this morning, and from what I heard, it sounds like we came through in flying colors, no recommendations. So that should be, hopefully, over with for the next 10 years or so. I won't be around to worry about it anyway, even if it's 5 years or 3 years or 2 years. Okay. All right. So anyway, that was good news. Now let's talk about what we're going to do in this course, in this class. Today we're going, like I said, hopefully finish chapter 4 and hopefully get started in 5. If we get far enough in 5, then we'll have time for a lab in 5 today. That's the first lab in, I'm sorry, not 5, 6. First lab in chapter 6. Okay? If we don't get far enough, then we're going to have a fairly long class today. Sorry about that. Tuesday, we will continue in chapter 6, definitely have a lab in 6, and have the test in 4, Tuesday. So 2 hours class, 2 hours lab, 30 minutes in test. And here's Diamond finally pulling up the bottom half of the alphabet. Way to go. So, Thursday, we will have continue probably in chapter 6 and have the second lab in chapter 6. That's my guess now. All contingent on how things go today and other days. Then we have the Thanksgiving break. And I don't know if y'all are aware of it, but you have the whole week off. We don't. We will be here, basically be on campus Monday, Tuesday, and Wednesday, but then the college is closed Thursday and Friday, Thanksgiving holidays. Now, a little bit of difference though. Usually we have meetings, almost always we have meetings on the Birmingham campus Monday and Tuesday of Thanksgiving week. So I will not be on this campus, or at least I don't think I will be at all Monday and Tuesday. Now also Monday and Tuesday I have eye appointments both days. So I will be, and they're early in the morning, at least my understanding they are, and so as soon as they're over I'll be going to the Birmingham campus. And the first one they said might be maybe 3 hours or so. So I might not get there until the afternoon. The second one they said won't be long at all, so hopefully I'll get there in the morning. But anyway, I won't be there all day Monday or Tuesday, but I'll be there the latter half of both days. And maybe more than half of the second day. Now, Wednesday, they usually let us come back to our offices. They usually don't have organized meetings, so I should be on this campus on Wednesday. Now, all campus offices should be open Monday, Tuesday, and Wednesday. So if you do have business to take care of at the college here, you can do so Monday, Tuesday, and Wednesday. Now, they may be short-staffed, but there won't be many students, won't be much business, so you should be able to be taken care of. However, on Wednesday, this is the Thanksgiving week, I would not come in late in the afternoon and expect to find offices open. They don't, they certainly aren't required to, and they don't always, but quite often they do let people go earlier on the day before Thanksgiving, just because there's not really a lot going on, and people want to get home and start getting ready to eat turkey. So do not plan to get things taken care of Wednesday afternoon. If you've got something, business to do at the college, get it done Monday, get it done Tuesday, or Wednesday morning. I almost guarantee you all offices will be open Wednesday morning, but if my memory's right, sometime afternoon on Wednesday, they usually start letting people go. So I wouldn't wait that late. All right. So that gets us through Thanksgiving. Let's get on to the week after Thanksgiving. That's the first week in December. Okay, if we haven't finished chapter 6 by then, we'll be wrapping up 6 then. We have one more lab on chapter 6. We have 3 labs on 6. The first one may be today. The second, okay. One of these days coming up, we're going to have a pretty long class because we've got left. We've done both labs on chapter 4. We got 3 labs on 6 and 1 lab on 8. Okay? The lab on 8, let's start working backwards. The lab on 8 will be Tuesday of finals week, and that's also when your test on 8 will be. Okay? So hopefully we'll be finishing chapter 8 by the Thursday of the first week in December. So that means we'll probably be starting chapter 8 Tuesday of that week. So one of those days is going to be a pretty long day. Maybe one of the days next week too. We'll see. I'll try to, if we're not going to have a lab, try to have that a day we also have a test. So at least you have 30 minutes without me talking at you. And it could happen to be that we'll finish chapter 8 a little early, and maybe, heaven forbid, y'all get to leave a little early. If we do that, we'll try to have that on the Thursday for you guys who have to travel so far. Okay, so we'll see if we can work that out. All right, so that's kind of how things are going to do. It's all in flux. So we have the test on chapter 4 coming up Tuesday. My guess the test on chapter 6 will be either Thursday of next week or Tuesday of the after Thanksgiving. And then the test on chapter 8 will probably be the Tuesday of finals week. Okay. And we'll scatter the labs in there wherever we can. The lab on chapter 8 will probably be that Tuesday of finals week. And then the final exam will be the Thursday of finals week. Sorry about the cough. Now, for some reason, my slides aren't right, because we did these slides before. Here's where we begin today, or at least that's my memory. Everybody correct with that? All right, so let's go from current slide. Any questions on anything I've just said? Anything else toward the end of the term? Anything that we've done so far? Anything on chapter 4? Anything? Any questions? All right. If not, we're entering this phase, evaporation and condensation. Okay? I was almost anticipating hearing a few questions about, well, wait, doesn't water evaporate whether it's at boiling or not? It doesn't have to be at the boiling point to evaporate, does it? Okay? So the answer is no. Water evaporates at all temperatures. It doesn't have to be at the boiling point or the vaporization point for it to condense. Okay? If you have a cold glass of ice water or something like that, and especially in the humid summertime, you'll see water droplets appear on it almost immediately. Okay? So evaporation and condensation doesn't wait till the boiling point or evaporation point. Remember, what's actually going on here is the individual molecules, what their kinetic energy is. Okay? If they are fast enough and powerful enough, their energy is high enough that they can escape, they will escape. So you don't have to be at the boiling point, because the boiling point is the average kinetic energy of those molecules. It's not what all the molecules are. Otherwise, all the water would boil at the same time. It would just and be gone. But it doesn't. Some of it's still liquid and some of it's boiling. Well, the same thing true below the boiling point. Some of the molecules may have enough energy to change phase at any time. Because remember, there's a whole range of energies in that one pan of water, say. So evaporation, the energy required to overcome the phase cohesion, that's all that's required. That individual molecule, if it's got that much energy, it's out of there, okay? Especially if it's near the surface, okay? The higher energy molecules near the surface can then escape, and that's what happens, okay? Condensation, the gas molecules near a surface lose kinetic energy to the liquid molecules and then merge back in, or on the side of the glass, okay? Now, so evaporation and condensation do occur at all temperatures, remembering temperatures are average kinetic energy. All it takes is for individual molecules to have enough kinetic energy to leave, to break away from that force of cohesion. So here's just a sort of a strange example. The numbers in here don't mean much except relative to each other. And this probably isn't completely characteristic, but at least it's it can be representative, okay? The numbers in here represent average kinetic energy, okay? So don't hold anything to the numbers. That's all they're representing. You have 4 that are very slow, very low energy molecules, okay? You have another 3 that are a little bit more energetic, but not a lot. Another 1 that's a bit more energetic. And then you have these 2 up here. These 2 up here who basically have enough energy to leave town when they get near the surface. Okay, they have enough energy to break away from that cohesive phase, that phase cohesion. Okay, and if they're near the surface, they will probably do that. Now, before they break away, though, what is the average kinetic energy of this representative glass of water? Okay, you got 50 here. 60, 70, 80, 95, 100, 105, 10, 15. 115 kinetic energy units divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 representative molecules. That's a pretty easy calculation to make. 11.5 is the average kinetic energy of that beaker of water. Okay? So that might be at near room temperature, let's just say. All right, but what happens here is these 2 do get near the surface, they have enough energy, they escape. Okay, well, what have we got now? We've got 15, 25, 35, 45, 50, 60, 70, 80. Only a total of 80 energy units divided by 8, that's down to 10. On average, energy units for this glass of water. Well, what does that mean? It's cooler. Okay? Actually, losing high energy molecules tends to cool your liquid. Okay? And you may have noticed that before. As water evaporates, you get chilled. Coming out of a hot shower, and the water starts evaporating off of you, you can get chilled fairly easily unless you have the heat pumped up pretty good in the bathroom, right? So that is exactly what's happening here. It cools. Now, in one physics book that I've taught from before, it had a picture of a guy, this is out west, pretty sure because the authors were out there. He was doing some rock climbing and stuff like this, and he had a canvas bag that he had his water in. Why a canvas bag? Because the canvas allowed the water to very slowly evaporate. Okay? And by evaporating, it kept his water cooler, so when he drank his water, it was more refreshing than if it was 80-degree water. You know, that's not necessarily all that desirable. Okay? And sure enough, people do that. They let evaporation do the cooling for them. So here was the second half of that. When you lost 2 and you lost 50, that got you down to, I miscounted. 65 divided by 8, which is 8.1. Somehow I missed that. 15, 25, 35, 45, 50, 55, 60, 65. I'm sorry, I missed that. 65 divided by 8, about 8.1. So it was 11.5, dropped down to average kinetic energy of 8.1. Now it's a little cooler, more pleasant to drink. Okay? The average drops with more energetic molecules missing. Okay. And that's also why run a sink of warm water and you come back after you eat breakfast or something like that, come back and the water is tepid. It's no longer warm. Those high energy molecules have escaped, making the water cooler. Okay. So there's energy evaporation and condensation. Now, in the text, a picture of a solar energy clothes dryer. You see it? They had them years ago. Hardly anyone uses them anymore. Solar energy clothes dryer, a clothesline. Okay? You know, this, by and large, I think the clothes felt better and smelled better back then, too. It was all done in the dryer. All right. Anyway, let's move on to 4.5, which is thermodynamics. Now, what does this prefix thermo mean? Heat, okay? Dynamics, dynamic, changing, usually changing rapidly. So this is the change, the exchange of heat, okay? Or, more proper definition, the study of heat and its relationship to mechanical and other forms of energy. Thermodynamics, how it interchanges with mechanical and other forms of energy. And even Ethan showed up. Okay. Top part of the alphabet is perfect attendance, and poor old Diamond is having to hold up the whole bottom half by ourselves. Okay. Thermodynamic analysis includes, and this is sort of key to thermodynamics, you look at entire systems. A lot of what we've been doing, that last slide, had us looking at individual molecules, high energy molecules escaping. Thermodynamics really isn't concerned that much with molecular or small scale, it's big scale stuff. So the whole system, not individual molecules. The system may include the surroundings, okay, everything outside the system, or at least the immediate things outside the system. Now, it's mostly concerned with internal energy, the total internal potential and kinetic energy of the object in question. Not the individual molecules, but the total internal potential and kinetic energy. All right. Almost completely new subject here. How do we do energy conversions? Okay? Now, how does a brake stop your car? Say again? Absolutely. Because you got kinetic energy of your car, right? And the brake pads and the brake drums, or whatever you call the pieces these days, that's what they used to be, when they press against each other, friction slows it down. Have you ever accidentally touched one of those shortly after it was brought into the shop? Pretty warm, as in burn your hand, right? That kind of warm, right? Hot, I would say. Very hot, okay? Why? You've converted the movement of the car by friction to heat. Okay? There's one. Friction converts mechanical energy into heat. Rubbing your hands together, especially if you press them together, that'll warm them up pretty quickly, even if they're kind of chilly in this room. Okay? So there's one energy conversion. Another, a heat engine. Basically, you're talking about your automobiles or other devices like that. Devices that convert heat into mechanical energy. Now, how does that happen? It's exactly what happens in your cylinders. You explode the fuel, and heat expands the gases, pushes down on the piston that's connected to the cams and the shafts and the various things like this, ultimately turn the wheels of the car. So the converting heat into mechanical energy. That's what these guys do. Okay. Now, other applications. Heat pumps. What does a heat pump do? It's the first stage of a heat pump. What?
You got to get your natural gas or propane, whatever you're running, you got to get it at night.
Okay. Now, heat pump, I'm thinking of.
You're talking about HVAC heat pump?
Yeah, that kind of thing.
Pressurized.
Say again?
Pressurized?
That's it. You pressurize your, it's sort of a strange name here, refrigerant, right? But we're not using it to refrigerate. You pressurize the gas, and when you add pressure to a gas, now that's mechanical energy, pressurizing a gas. What happens when you pressurize a gas? It heats up, okay, just like friction. And it is very much like friction. Well, what you try to do then with your heat pump is get that heat to blow into your house or the space or whatever, and that's what you use to heat your house, okay? Our upstairs unit on our house is a heat pump, okay? And the downstairs unit is a heat engine. Well, not really a heat engine. It's just a natural gas heater. So, that's what a heat pump does. How is that similar or different from a refrigerator? Or an air conditioning system?
Are you running an ammonia refrigerator?
Okay, whatever you got in it, whatever the refrigerant is, you start the same way. You pressurize the gas, creating heat. Now the difference is with a refrigerator, you blow that heat off the coils in the back of the refrigerator. It used to be sometimes underneath or on top of refrigerators in the very old models. But you get rid of that heat. And then you let the gas expand quickly, and whereas compressing it produced heat, expanding it absorbs heat. And that's what does your refrigeration, freezer, air conditioning. Okay? It's just the next step in the heat pump. The heat pump compresses and uses the heat. The refrigerator compresses, blows off the heat, and then lets the gas, the liquid, whatever it is, expand, and that's what creates the refrigeration. Now, this one's a little weird. Organisms, okay? Well, organisms, like us, we consume a fuel, carbohydrates, hydrocarbons, proteins, whatever, and we burn them. We're heat engines, okay? And so that's another application of energy conversion. We take in stored chemical energy, chemical potential energy, process it, and give off heat. At the same time, we're making our motions, reading our books, listening to instructors, well, some, okay. Now, what does a hurricane do? Does it do something? Hurricanes absorb heat. Where do they begin? Say again? Low pressure areas where? Over what? Ocean? What part of the ocean? The what?
The Atlantic.
Well, Atlantic or Pacific.
Yeah.
Say again?
It's usually in the middle of the ocean.
You got it. Well, when you say in the middle north to south, around the equator, always, all your hurricanes start there. Even Sandy that hit in New York and New Jersey a few years ago, that started in the tropics. They always start in the tropics. They don't start in the cooler part of the ocean. That just doesn't happen. Mark is here.
Good afternoon, everyone.
He does happen. Okay, good deal. Now, and what the hurricane does is absorbs that heat, and as it absorbs the heat, okay, low pressure happens because the heat rises. Remember, stack effect, heat rising, convection, heat rising creates a low pressure area. The low pressure area creates spin motion, and that's what creates the spinning of the hurricane. Okay? Stars are enormous heat engines, okay? They've got thermonuclear reactions going constantly, okay? And they are producing lots of radiation. So we have stored nuclear energy becoming electromagnetic radiation. Black holes, who knows what they do? Okay, some of you know more than others maybe. But a black hole is absorbing energy constantly. Now, they have figured out there is energy escaping from a black hole. It's usually just not light energy. Okay? Virtually any system with energy inputs and outputs, that's using thermodynamics. Again, we're thinking macro scale, not micro scale, macro scale. Okay, any questions? Thermodynamics. There are basically considered to be 3 laws of thermodynamics. We're only going to touch on 2 of them. Many people claim there's a 4th law, but they don't call it the 4th law. They call it the 0th law, because it's the one that everything else is built on. But when they developed it, they only came up with 3 to begin with. Someone said, well, you know, you're missing the fundamental one. So that was the 0th law. The others are 1st, 2nd, and 3rd. Here's the 1st law of thermodynamics. Basically, it's a statement of your conservation of energy. Okay? Here are the components of that energy. Some of that energy is in internal energy. Internal energy within the body, whatever the body is. It might be the compressor, it might be the piston, it might be wherever the energy is. That's the internal energy. Okay? Then you have the heat. Usually heat is something given off. Sometimes it's absorbed, other times it's given off. And then you have work. Okay? Now, most of the time, work is done by the system, like moving the car, but sometimes work is done to produce it, like compressing the gas. So you have all these 3 components. Internal energy, which can be increased or decreased, heat, which can be absorbed or emitted, and work, which is either done by the system or on the system. So all 3 of these could be positive or negative. Okay? I wish they showed the equation first, but they show the illustration first. Well, actually, yeah, it's okay. Here's a system. This is a simple heat engine. You're using heat to do mechanical work. Okay? So this should have been back on the last slide. Okay? What you have is a cylinder with a piston in it that doesn't allow the gas to do, and it sits there. But then you put a weight on it. The weight compresses the gas. Okay? So you're okay, the air in there gets compressed a little bit. Well, then you put a flame under that. Now this heat that the flame is sending there, that heat here is now doing work on the weight by pushing it upward. Because the molecules move faster. You're not adding any molecules. In fact, this picture is not very good. These molecules should be much more closely together. This should be the same number of molecules here as here. It's not. If they had drawn this properly, there'd be just a mass of molecules here. You add heat, those molecules just spread out because they're moving faster, they have more internal energy, and they bump into each other, including the piston, and push it up. Okay? So this is a sample of a heat engine. Heat is doing mechanical work to the weight. Okay? Now, and by the way, conservation of energy, the amount of heat that you add here, as long as there's no loss to the environment, remember we talked about the environment being part of it too. As long as there's no loss to the environment, all the heat added is used for work in lifting the weight. Now you know that never happens. You never have a totally efficient heat engine. In fact, most of the time they're pretty poor. What would you say the efficiency of an average car engine is?
31%.
Okay, they've gotten much better over the years. It used to be in the 20s. Okay? That means 70% or 69% of the energy that car is produced is wasted to the environment. Okay? Some of it's blown out the tailpipe, some of it is blown out of the radiator, blows off the fluids that are circulating there. Others heat on tires on the road, all sorts of things. Just not a very efficient machine, but a very necessary machine. Okay, so there's the first law of thermodynamics, conservation of energy. As long as there's no loss to the environment, all the heat added here would do work on the equipment. But even conservation of energy, if there is heat loss, friction, just heat loss to the environment, you still account for it. Okay? Energy is conserved. You can't create it, you can't destroy it. So here is the illustration of a heat engine. Okay? All right. Again, I wish they showed the formula first. They're going to get to it in a minute. If they don't, I'll write it on here. But it's stated in terms of changes in that internal energy. Changes of internal energy are either due to heat being added to the system or lost. Work being done on the system or by the system. That's how you relate. What is changing your internal energy? And how is it being changed? So here is an example of a heat engine. All right. Think of this as your piston, okay? Just to use that as an example. That's a high temperature region, okay? This expansion, the high energy here is used to produce work, to turn the wheels of the car, okay? That's what the heat engine does. However, there's some low temperature region down here. That's where some of this heat is lost to. The tailpipe, the cooling system, okay? The various parts of the car, friction, rubber on the road, or when you brake the car, there you lose more because you're changing the kinetic energy you were producing here back into heat again. So lots of low energy region down here. The heat always flows downhill, okay? From high energy to low energy, under normal conditions, under natural conditions. Are they finally going to give us the formula? No, they're not. Shame on them. I thought they were going to, but they didn't. Let me write it for you, okay? It's given in your book as equation 4.7. Okay. Now, let's go back to this figure. Here, not quite. That's just your heat engine model. Okay, let's do the formula. JQ, let me get to a light color. JQ. Okay? Now that's a strange representation. What that means is the joule equivalent of heat. Q is usually heat. Remember, we did this in lab. And the J is, convert that to normal energy units. Heat is usually in calories or BTUs. Get it into normal energy units, which would be joules or pounds. Okay? Or Ryan's. Okay, whichever. All right. That's your heat. That's the heat part right there. Minus W, that's the work, okay, is equal to, okay, U2 minus U1, okay? That's the change in internal energy. And you see there's a difference there. I would have written that delta U, change of internal energy. So U is internal energy, 2 is the, however you want to do it, final, 1 is the initial, that's the change of internal energy. Now remember, all of these things could be either positive or negative. If the heat is being added to the system, like lifting the weight, then this would be a positive quantity. If W is the work being done on that weight, okay, that would be done by the system, that's your minus, okay? But if you're doing work to the system, like the compressor does, you compress the gas, now you're adding a positive here and raising this, okay, so it all, and that's your change of internal energy, okay? They're all related in some sense there, okay? So there's your basic formula for the first law of thermodynamics. It's a conservation of energy. Change of internal energy is either to the joule equivalent of heat or work. Plus or minus one or the other, that's what's changing your internal energy of the system. Okay. Now, let's move to the second law of thermodynamics. Now, this is sort of a strange one. It has 3 equivalent statements here. Some of these are a little vague in my mind, and some of them don't really seem like they're equivalent with the others, but indeed they really are. Here's one way of expressing that second law of thermodynamics. No process can solely convert a quantity of heat to work, like in your heat engines. Sometimes they're as inefficient as 31%, okay? But other times they might be a little bit better than that. And sometimes they're far worse. No process can convert 100% of the heat to work. It just doesn't happen. Second law of thermodynamics. Now this one seems a little bizarre. Heat never flows spontaneously from a cold object to a hot object. That just doesn't happen, okay? Now that seems like it's not even saying anything close to these other two, but there really is a connection there. In other words, it's saying heat always flows from hot to cold in spontaneous manner, under normal circumstances, from hot to cold. And your refrigerators are doing that. Even though you're creating cold, you have to get rid of the heat first. That's where on your refrigerator, those coils in the back of it is usually where they are nowadays. At one time they were underneath. It wasn't a good place for heat because it went up, so they put it in the back. I can remember the old refrigerators, that thing was up on top, okay? That wasn't very attractive, so they got it in the back so nobody sees it, okay? But anyway, you have to get rid of that because it never spontaneously goes from cold to hot, okay? And the third, natural processes tend toward a greater state of disorder. This is how I see it referred to most of the time in, say, physics books and things, the entropy of a system, the disorder of a system, always increases. Unless you add energy to it. Then you're not spontaneous anymore, you're forcing it into order. Okay? Natural processes always tend toward greater state of disorder, increasing the entropy. Entropy never decreases spontaneously. Okay? It always is increasing. Now, here's some really dumb examples of that. Let's say that we bought a package of brand new playing cards. Okay? Anyone ever open a package of playing cards? Okay? How are they using cards in there? I bet you the top card is usually an ace or a king, and then the queen, probably in spades, and then the queen, jack, 10, 9, 8, and down to the deuce. Maybe the ace there. It's one or the other. And then you have your hearts. And then you have your diamonds. And then you have your clubs, right? All in those orders. They're all in perfect order. Okay, let's take that deck of cards out of the box and put them on a blanket here. And we'll get around the blanket and we'll toss them in the air so that they all fall on the blanket. Okay? And by the way, all those cards are facing the same way too, right? The face is down, the back is up, right? All of them like that. So we throw them up in the air. Okay? Now how many times do we need to throw them up in the air? Do you think they'll come back in that same order? No. Unless you glue them together. No, okay. They will not. Okay? How many times does it take to throw them up in the air until they do come back, happen to come back in that very same order? Never happen. They just get more and more disorder. Always greater state of disorder. Some of them will be flipped over, some of them this way, they will be mixed up. They never go back to a greater order. They always go to greater disorder. Now that's one way of looking at it. Here's another way. All right. All of you have rooms at home, right? Do they ever get neater just day after day after day? Really? You mean they get more disorderly? Unless you put energy in the system to clean them up. Everything tends toward disorder in a natural system. Okay? Natural processes. They just go to disorder. And then they have another one somewhere here. Maybe it's on the next slide or somewhere else. Have you ever spilled milk off the table back into the glass? Don't think so. It always goes to disorder, never back to order again. Okay? That was one of their dumb examples. 2 for reference scales here. What we do is look at the object's external energy. That's the energy of the global coherent motion. I throw the baseball to you. The motion of the baseball, the kinetic energy of the baseball. Okay? That's the energy of the global coherent motion. That's associated with work, the work it took me to throw it at you. Okay? Oh, to you. Okay? Then you have the object's internal energy. That's the energy of the microscopic, chaotic, incoherent motion that's going on within that baseball. Okay? That's associated with heat. Okay? So baseball probably wouldn't be the best example, but say you had some type of fluid that just the spinning of the ball or whatever you're throwing happens to make it get hotter. Okay? That would be internal energy. The motion of the coherent motion, kinetic energy, would be mostly the external energy. Okay? Associated with work, disassociated with energy. This is really getting back to that first equation we had, almost. Okay? So let's look at these 3, this is where it's coming out. These 3 statements again. The first statement was, no process can solely convert a quantity of heat to work. Okay? That basically is conservation of energy again. Your energy, your input energy, has to always equal your output energy. of energy. Whatever you put in, that comes out. However, this output is not always useful. A lot of it is wasted. Okay? Unproductive energy. Not useful work. The efficiency of a heat engine is the work done per unit input energy. So you have input energy, that's all you're putting into it. The output energy is split. Some of it is useful work, some of it is wasteful energy. So the efficiency of the engine is the useful work part per unit input energy. The second law says, in one way, efficiency can never equal 1. You're never going to get all the useful work out of it that you put into it with input energy. Just isn't going to happen. Okay? Some energy is always degraded into non-useful energy. Okay? Generally, that's wasted heat. Okay? The car moving down the highway, if nothing else, is bumping into air molecules. That creates friction. Okay? That retards the motion. Okay? It speeds up the molecule. If you had really sensitive thermocouples around, you see that the temperature of those air molecules right next to the car is greater than the temperature out here. Not by a lot, but by a little bit. There's always wasted energy. Okay? Degraded energy. All right? Here's the other way to express this. If you go back to this figure, here's your input energy, the QH, input energy, high temperature region. The work coming out is the W over here. The QL is that low temperature region that you didn't get any work out of this. Okay? So your energy is, your useful work is W, your input was this, the ratio of W to QH, always less than 1. Because some of this energy went down here. So with that in mind, here we have it. QH is equal to W plus QL. That's exactly what we saw here. QH, some of that is work, some of it is what? Low energy region. Okay, low useless energy. Okay, that you wasted. Okay, the work is here, the low energy there. So there is the first part. This is conservation of energy. All the energy you put in, some of it went to work, some of it was wasted. QL. Conservation of energy. Okay? Your efficiency then is this part divided by that part. Since this part is never zero, and certainly never negative, never zero, never negative, this is always less than that, so E is always less than 1. Cannot ever equal 1. Certainly can't be more than 1, but it can't equal 1. Okay? Here's the second statement. Let's go back to the second statement. Okay? Heat energy never flows spontaneously from a cold object to a hot object as in refrigeration. So here's the second statement. Now this time, you're having to do work on the system to take this low temperature region, gas, and move it up here. That's what your compressor does. Okay? You do work on the gas down here. You supply the work. You either are pumping, your compressor's pumping, something's doing work in, increasing this, moving it up here. Okay? It never moves there by itself. Ever. Okay? Never. You have to do work. I don't like this drawing. I would put the work down here and move it up here, but you get the same. That's what this is mean. And this is what your heat pump is doing. It's taking the energy that's already in that I'm going to call it refrigerant because that's what we usually call it. the gas that's going to be compressed. You take that, the work compresses it, produces heat, that's what you're blowing out. Okay? The energy arriving in the high pressure region is equal to the energy that was originally here plus the work you needed to move it up here. Upgrading of energy by a heat pump is accompanied by greater degradation in energy somewhere else. Okay? Because even to do this work, let's say a compressor run by a gasoline motor, electric motor, somewhere there is actually degradation just to do this work. Okay? Those compressors get, well, the compressor, the compressed gas gets hot, but just the thing that's pumping, that's doing that, there's heat produced there as well. All right. The third statement. Okay, remember the third statement? Natural processes tend toward a greater state of disorder or entropy. Now, this is the one they gave their statement to. Okay? Real processes are irreversible processes. Okay? Have you ever unburned any fuel? Nope, not going to happen. Okay? Closest thing we get to that is when the little leaves out here take out the carbon dioxide that you exhausted before and turn it back into simple sugars, which later might become an oil or something like that. But that's a long way from what that. Real processes are irreversible. You can't go backwards. The measure of disorder is called the entropy. So the other way of saying the total entropy of the universe continually increases, meaning the disorder of the universe, which is sort of a scary thought, isn't it? Okay? Because that means at some point it runs out, okay? Not in our lifetimes, hopefully, okay? So the second law in these terms, total energy continuously increases. Entropy increases. Now, another way to express this, natural processes degrade coherent, useful energy. Okay? Natural processes don't do any good to that. They degrade it. The available energy in the universe is diminishing. Okay? There's just a whole lot of it out there. Okay? Eventually, the universe dies of a heat death, as do most stars. Okay? They die sooner than the universe does. We don't know how the universe is going to do it, but it's done. Okay. Now, the direction of natural processes is always toward more disorder, entropy, higher entropy. And this is their example. Spilled milk will never unspill itself back into the glass. Doesn't happen. Or the broken glass, you can throw it down on the floor as many times as you want, and it's never going to reform a glass. Okay? Just doesn't happen. It'll just splinter into more and more pieces. Greater and greater entropy, disorder. All right, and that is the last slide. So let me go back and tell you what the third law of thermodynamics is. We talked about this back in the heat section. The third law of thermodynamics is absolute zero may be approached but never reached. You can get close to it, you can never get there. And the book actually gave an example, I think, of someone getting within a few hundred billionths of the absolute zero, but never could get there. How in the world do you measure a few hundred billionths of a K? I don't know, but that's what they said. Okay? That's the third law. The absolute zero may be approached, but never reached. Okay? Now, the zeroth law, by the way, is basically something like this. If you have object A and object B, and they're both in thermal equilibrium with object C, they're in thermal equilibrium with each other, even though they're not touching. A is touching C, and it's in thermal equilibrium. C is touching B, they're in thermal equilibrium. That means A and C are in thermal equilibrium. It's a really simple concept, and that's why they didn't even think of naming that as a law. But some people have suggested that needs to be the zeroth law. Because guess what? You can never measure temperature if you didn't have that law, right? You stick that thermometer in your mouth is touching the glass bulb. The glass bulb is touching the mercury or whatever's in that thermometer, and that's what makes the mercury go up. You don't put mercury in your mouth, so if object A is in contact with object B, object A is your mouth, object B is the using to measure your temperature, object C is the glass in between. So it's a real simple concept, but that was the zeroth law. Not that you need it in this chapter. So, last slide. Before I get to the end of the chapter, there is a mistake, and misunderstandings. Ever heard of a Rube Goldberg machine? That was some guy came up with a thing that it operates itself and never stops. It's a perpetual motion machine. Never happens. Second law says it can't happen. Can something make its own fuel? Not going to happen, okay? I think they tried that with the converter. Now, if you can use some wasted energy to make fuel, that's an improvement. And that's what they do with regenerative braking. They, rather than producing heat, you produce electricity by having very strong electromagnets that you're forcing to spin, and that's what you use to brake the car. But those electromagnets spinning, that produces electricity, which you can then use to generate the car. You ever get all of it back? No. Never. Now, the person behind the science that's mentioned here, really attractive fellow, isn't he? Count Rumford. His name was actually Benjamin Thompson. And notice the years that he was born. That he lived. 1753 to 1814. What happened during those years? 1753 to 1814. American Revolution, 1776. And actually, that's how he became a count. Because he was U.S.-born physicist and engineer. He first demonstrated conclusively that heat was not a fluid, which they thought it was, an ethereal fluid that lived in materials, or was in materials, but it was actually a form of energy. They say of motion. Now, how did he do this? Have I told you this story before? He was, I'm going to come back to the earlier part now, later, but let me tell you this part now, because this is most important what we're doing. He was an engineer who did work wherever they needed engineering work. He was actually working for probably the Holy Roman Emperor or somebody like that, making cannons for whatever was existing as the German state, perhaps Bavaria or whatever, okay? And he was boring cannons, okay? What they used to do, they took iron, they mined from the ground, they smelted it, became pure iron, basically something like cast iron, and they poured it into a cast that was the shape of a cannon barrel, okay? But they couldn't make the hole, so they had to bore the hole out, okay? So what he was doing, poor old dray horse was carrying this, going round and around in circles, and going around and around a circle, was turning a bit that was grinding out the cast iron to make the cannon barrel, okay? Now, he notices he did this, especially when the bits got older and a little bit duller, they produced more heat. Now, everybody up to that time said, well, the heat exists in the metal. Remember, you just smelted it. There was some heat still trapped in there. That's what produces the heat there. He said, no, I don't think so, okay? So what he did, he took the dullest old blade that he could find, okay? Boring tool that he could find, and a bore that just didn't work right. I don't know why, but it was wasted. And he had to bring down ice cold water from the Alps. That's why I think it was Bavaria. I mean, really cold water. Put the cold water into the barrel. You would do this on a real barrel, that would make it rust. But he put it in there and got the horse to circling around with that really dull bit. And within an hour, he had that cold, ice cold water boiling. Boiling, okay, without any fire being added. He said, look, this is not the result of some ephemeral substance that lives inside the cannon or the water or anywhere else. This is from the work that poor old horse is doing, turning around and around and around because of the friction of the dull blade bit on the hard old metal. He was the first to discover that. James Prescott Joule then took that discovery and refined it and quantified it. Okay, let's go back to Benjamin Thompson. How did he become a count? Well, as you said, the American Revolution happened then. Benjamin Thompson, I think, was living somewhere in upstate New York. No, New Hampshire, okay? And guess what? He didn't believe in independence for the American colonies. He thought we should still remain British subjects. I mean, Britain was the strongest power on the earth. Why would we want to break away from them? So he supported the British. And I think he may have even had some connection with, what was that guy's name? Benedict Arnold, I believe it was. What happened to him? Huh?
Ain't he the one that was the traitor?
He was.
Yes.
And what happened to him? He was executed. I think about that time, Benjamin Thompson said, I think I'll move to heaven. Okay? And he did. And because he came over to the right side, the British thought, they gave him a title, Count Rumford. They could give away counts anytime they wanted to. So that's how he became a count. We didn't have many Americans becoming counts, but he did. Yeah, he was, no, actually by the Holy Roman Empire. I'm sorry, I got it wrong. I thought Britain did it because of recognition for the civil administration work he did in Bavaria. So I was right on that part. So anyway, interesting story. By the way, of this class of 13 of my brightest students ever, 1, 2, 3, 4, 5, 6, 7, 8, 9, I have received 2 papers. 2 out of 13. Now 3. Okay, 1 came in today. Guess what, folks? You only got this weekend, next weekend, which includes Thanksgiving week and that weekend, and then 1 more weekend, and that's all, folks. So please get working on your papers. All right, there's a potential paper topic. Several potential paper topics right there. All right, I also need to go back 1 slide here, and let's say, example 4.8, a heat engine. Now this is a heat engine. Going back to first law of thermodynamics, I think. Heat engine operate, no it isn't, okay. Yeah. Heat engine operates with 65 kilocalories of heat supplied and exhausted 40 kilocalories of heat. So you have 65.0 kilocalories of heat input. That's your H, Q sub H. You have 40 at the end, 0.0 kilocalories of heat exhausted. That's your Q sub L. Okay? How much work did the engine do? Pretty easy mathematical thing to do. What is it? How much work did the engine do? It took in 65 kilocalories of heat, exhausted 40 kilocalories of heat. How much work did it do? Help me, somebody. What does it appear? You had so much heat input, so much heat output. Where did the rest of it go? It went to work. How much? 25? Okay, 25.0 kilocalories. But is that how we usually measure work? No, we measure heat in kilocalories. That's what we're measuring down here. What do we measure work in? Say again? Joules. So we need that joule equivalent of heat. Do you remember what that was? You need to have a space base equals blank joules. We need to get it to joules. First tell me, actually I like to get it to kilojoules. Okay? I'm going to get it to kilojoules. Because this is in kilocalories. Why change it to joules? The book does, but we won't. So we need to put one of these units on the top, one on the bottom. Which goes where? Somebody help me, huh?
Joules on top.
Kilojoules on top, perfect, and kilocalories on the bottom. Okay? And what's the joule equivalent of heat between those two? Okay? I think you'll see, if you look in the book, 4.184 kilojoules is 1 kilocalorie. Okay? So multiply 25 by 4.184 and what do you get? Anybody have a calculator? One, 0, 6, no, 4, 6, huh? Is that what? 104.6. Okay, how are we on significant digits? We only have 3 input here, 3 input here, 3 input here. Even though we got 4 here, that doesn't count. We go with 3, so what was this round to? 105 kilojoules. And that's what they probably give in the book. Except that, yeah, 105 kilojoules. Now, they took it to joules and had 104,600. Why? Just go directly to kilojoules there. Okay. Now, the question they didn't ask, and let's ask it now, what was the efficiency of that heat engine? What would be the efficiency? This was work out. That's when you go and lift weights, work out. No, never mind. Okay. So what would be the efficiency? What was E? Anyone remember? E is the work divided by QH. What was our work here? Let's use the kilocalories. You need the same units. So what's that? 25.0 kilocalories, though we changed it to kilojoules, divided what was the input energy? 65.0 kilocalories. You have to have the same units for that to work. What do you get? 25 divided by 65? 28? 38. Or 38%. Heat engine is 38% efficient. Pretty poor, huh? All right. Anyway, we've done the last problem. There is a thermodynamics in action, which is sort of redundant because dynamic means action. But anyway, you can read that and certainly do that. If you got an electric blender and a thermometer, please don't get the thermometer caught in the electric blender. You're going to have some mercury contamination or alcohol or glass contamination, so don't do that. Okay. Anyway, nothing replaces reading the chapter. Please read the chapter. I hope you've already read it maybe once or twice before I got to it. But then, after you've read it, the summary is a pretty reasonably sized summary. quite a few italicized words. There is a summary of equations, 8 equations listed here, and some of these can be rearranged to be more equations. Key terms is a fairly short list here, but anyway, pretty good list. They're listed alphabetically, but they do give the page numbers where the concept is first defined or described. Then applying the concepts, and again, a fairly short list here, only 43 multiple choice questions, but I think the very best tool for studying for your test. Okay? You certainly won't have any of these exact questions on the test, but you'll have things that are similar to it. Okay? The answers are given, so don't look at the answers. See if you can figure out what you think the answers, see how you do. Then the questions for thought, 17 of those, that's about a normal number. 7 for further analysis, that may be slightly more than normal. There is a who can last longer. I'll let you read that if you are interested. It's sort of an interesting thing to think about. And then you have the parallel exercises that if you did have the answers in the book, the Group A would have answers, Group D never do, but I don't think they put them in your book anyway. All right, too bad we can't do Chapter 5. We just don't have time. It's far more important that we get to electricity and magnetism, because all of you deal with that at some point, and that we get to a little bit of chemistry anyway, so that will be the last 2 chapters. So we're going to skip Chapter 5. You don't even have it in your book, and you move straight to Chapter 6. Any questions before we leave 4? The test for 4 will be the last 30 minutes on Tuesday. Okay? So let's move on from here. Discard that, can that, and go to Chapter 6. One of these days, the PowerPoint may open. Here we go. All right, we'll go from current slide. Chapter 6. They say the title is electricity, but as you'll see, it's electricity and magnetism. Because frankly, these go hand in glove. They go together. And their picture is not of, well, it is of electricity. Yeah. Now, it surely looks like this lightning strike initialized from the cloud and moved to ground. An incredible picture, by the way. However, some of these strikes that you're seeing out here could have actually started at the ground and gone to the cloud. We'll talk about that later, or we did in 111, those who were in here. Okay? The core concept here, which is on my page 140, I don't know what it is in your book, it's electric and magnetic fields. See, the two of them are together. Electric and magnetic fields interact with each other and can produce forces. They do produce forces. Okay? We call it electromagnetic forces. Now, we talk about electric forces, we talk about magnetic forces. We talk about electric fields and we talk about magnetic fields. But in reality, it's the electromagnetic forces and fields that really are the things that are most important. So here are the basic concepts. Okay? Now, you'll see some of these names here, and some will show up again in Chapter 8 when we're doing the beginnings of chemistry. So get used to them. They're in both places. And some of the almost the same illustrations will be there. So here's the basic concepts of electricity. Long before anyone really understood anything about electricity, they knew it happened. They called it an ancient mystery, was the amber effect. What that means, does anyone know what amber is?
The tree sap?
It's what?
Tree sap?
A fossilized tree sap. Okay, tree sap that over time, pressure, heat, various things, has become very soft. Tree sap itself is a sticky liquid. Don't want to mess with that. But once it's fossilized, and it's a very pretty color, amber, okay, and you have these rods of amber, okay? And they found out that if you took wool or fur and rubbed it on the amber and then reached over and touched diamond with it, it would shock her, okay? And that was a great parlor game. Ha, ha, ha. Wasn't that fun? Okay, now, that's about all they understood from it. They didn't know why. They didn't know why amber had this mysterious effect if you rubbed it with wool, okay? Along came, I believe he was British, J.J. Thomson, okay? He identified these negatively charged electrons. They are the culprit here, okay? Negatively charged electrons. Now, I don't think people really understood where they came from or anything else, but they were the things that shocked diamond, okay? Negatively charged electrons. What had happened, the fur had lots of these, or wool or whatever, had lots of these electrons, and you rubbed it on the amber and they were transferred. The action of rubbing, the work that you did rubbing, transferred some of those to the amber, okay? Now you had an excess of electrons on the amber. When I touched diamond with it, they jumped off and shot you, okay? Like a little lightning strike. I've noticed this several times, and I get a kick out of it every time. It just shows how little it takes to entertain someone who's in physics. But we have cotton sheets on the bed, but we have some sort of polyester blanket. And I notice that every time when it's dark and I pull the blanket back, I see little pricks of light, okay? Little lightning strikes, okay? Because of that same type of effect. I've also felt it before, especially when our dog is fairly clean, which is not all that often, but when she's clean and dry, which is not all that often either, and I go out and rub her, I can feel the little tingles because I'm rubbing electrons off of her or whatever, okay? So these are the negatively charged electrons. They are the culprits in shocking people. Okay. Now, today we have a much better understanding than they understood nothing back then. The basic unit of matter is the atom. Okay? Now, but atoms are made up of other particles. Now, sure enough, good old Democritus said that atom is indivisible. That's what it stood for. Smallest piece you could get of any material is an atom. Okay? Or some materials, elements anyway. Okay? But now we know that atoms are made up of smaller pieces. The difference is, for that to remain iron or copper or whatever it is, the smallest piece it can be is an atom. If you break it into smaller pieces, you just have pieces. It's no longer copper or iron or anything else. So the atoms are made up of constituents. Some of those constituents are these negatively charged electrons. Okay? Now these negatively charged electrons, okay, let's just say that we have an atom here on the desk. Let's just say it's about this dimension, about the size of my globe back there. Okay? Now I can't make my fist small enough to represent the nucleus that would be inside there. Okay? And then the electrons are taking up all this space around it. So maybe I need something way bigger than that. Say a ball that reaches from here to there, you know, really big ball. Still my fist is too big, okay? That would be the nucleus. The atoms are just flying around that nucleus. Now, what is about the atoms? The atoms are almost massless. They have a tiny, tiny, tiny amount of mass, okay? Very tiny, okay? The nuclei, the nucleus there, contains protons and neutrons. We haven't quite gotten there yet. That's what they do. Those are very, very, very massive. I mean, incredibly massive. One proton, one electron. The electron is about 1/10,000th of the mass of the one proton. And yet they have equal charges. Proton goes a negative, the electrons are negative, the protons positive. Equal charge, but very, very different masses. Incredibly different masses. Okay, so you have positive charged protons, and then those neutrons that are in there are ever slightly even more massive than protons, almost the same. They have no charge at all. Okay, so you have these negative electrons that take up almost the entire volume of that atom. Okay, and positively charged protons and neutrons that have enormous mass, but they take up a tiny, incredibly tiny little speck of volume, but they have all the mass to speak of. These electrons all put together don't come close to what one proton would have. Okay? And you got a bunch of protons. Okay? So this is the figure as they show it. Now, there's a couple things I don't like about this figure, but we can live with it. If this is your cloud of electrons, and that's why it's sort of fuzzy, because that's all it is, it's a cloud. Guess how many electrons are in that cloud? If you got 2 protons, you have 2 electrons. So this cloud is made up of 2 tiny little electrons with almost no mass at all, but they take up the bulk of the volume, and then this is way too big a dot, by the way, that's where your nucleus is. Now take that nucleus and blow it up, and you see 2 protons and 2 neutrons. Now that's not how they're arranged, but they're in there. This happens to be a helium atom. They haven't told you that, but that's what it is. It's the only thing that has 2 protons, and it happens to have 2 neutrons. That's why you had to have 2 electrons, because now, what's misleading about this, you really shouldn't have this outer circle here. The entire thing should be this vague cloud here, because you don't have 2 energy levels, there's only 1. And that's just circling that nucleus. Just makes it look like you have some in here and some out here. You only have 2 and they both live on the outside. Okay, so that's the makeup. As we said, the electrons are negatively charged, the protons positively charged, neutrons no charge at all, neutral. That's where it gets the name neutron. Now, why did I say the electrons are the culprits for shocking diamond? Couldn't it have been proton shocking it? We hope not. In order to get a proton out of the nucleus, you have to have a nuclear reaction. And we don't want those, okay? Those are really bad things, okay? So it's always the electrons that are moving, either gaining or losing. Helium never will lose one, never will gain one. It's happy just the way it is. Most of the other elements, they're happy to gain or lose, but not neon, argon, helium, krypton. I did say helium there, didn't I? I think I said neon one time, but it's another noble gas, but it's not that one. That was helium. Okay, so what in the world is our electric charge? Well, we're not going into great detail on this, but the charges in matter are inseparable property of certain particles. We've already said this. The electrons have the negative electric charge, the protons have the positive electric charge. Neutrons have no charge at all, so they're not at all involved with electricity. Okay? They're there, hanging around. Now the charge interaction, that's your electric force. And like I said, we're going to talk about electric forces, we'll talk about magnetic forces, but in reality it's electromagnetic forces. But here's the worthy saying, it's just sort of a cliche, but it's true. Like charges repel each other, unlike charges attract each other. Now what 2 types of charges do we have? Okay, so what would 2 positive charges do? Repel each other. What would 2 negative charges do? Repel each other. What would a positive and a negative do? They attract each other. Okay, so, and they will definitely do that. Now, we get to another issue here. What if that atom does like the amber, when I rubbed it with the wool, and fur, the amber picked up electrons. Now, amber isn't an element, but the atoms that make up that, they are no longer atoms. They are ions. A charged atom is an ion. And guess what? In the fur, those are no longer atoms. They're not really atoms of fur. Fur is not an element either. So that would be ions in the fur. Okay? Because ions are non-zero test charges, either from the loss or the gain of electrons. How about the loss or gain of protons? Doesn't happen. Okay? You don't have nuclear reactions. Okay? We don't. They're always the electrons that are being exchanged. So when they gain electrons, they become negatively charged. When they lose electrons, they become positively charged. So your ions are either, they're atoms that have either gained or lost electrons, never protons. Okay. Now, here's another representation of an atom. Again, the nucleus is way too big, but the electron structure is far better here. This happens to be a lithium atom. How do I know that? It has 3 protons. And the only element that has 3 protons is lithium. Now, if it has 3 protons and it's a neutral atom, it's got to have 3 electrons. Now, this happens to be very well described here because you have 2 electrons in the inner shell. That's where helium's 2 electrons lived in the inner shell, the only shell. But now when you add a third one, it moves to an outer shell. Okay? So the third electron is in an outer shell. Now, it's awfully lonely out there, isn't it? Way out there, away from the nucleus, away from the other electrons. It's really lonely. So if it has a chance, it sometimes flees, especially if it sees some other atom that happens to have a lot of protons, and it may just go in and get around that. Actually, gets around those with. Electrons are pretty romantic, actually. You see, if there's an unpaired electron over here, this one will want to go and get together with that one. So they get together like that. All right? And if that happens, you no longer have that electron here. So this is no longer a lithium atom. What does it become? It's still lithium, still has 3 in the nucleus, 3 protons in the nucleus, but what does it become? An ion. This is a positive lithium ion. And we would express that as, let me get my pen set up. You don't have to know this, but I'm just going to give it to you now. Okay. It would be Li plus. It would be a 1 plus charge lithium ion. Okay. Lost its outer electron. Now, there's a good chance, I'm just making this part up, that lithium electron went over and happened to get tied up with a chlorine atom that had 1 unpaired electron in it. And now those 2 electrons got together, they made a happy couple. But now the lithium being positively charged, the chlorine being negatively charged, they're drawn together and form lithium chloride. On Star Trek, dilithium crystal. No, that was something else, wasn't it? Okay. But that's what makes a positive lithium atom. Now, this never happens. Not with lithium. It happens with other things, but not with lithium. But let's just imagine it, because they didn't want to draw all the pluses in there for something else. If you did have 3 protons in your nucleus, it had to be lithium. If it did pick up an extra electron, which it won't, now it becomes what? And it never happens. What is it? It would become an ion. This would be, if it ever happened, a lithium minus ion. It doesn't happen, okay? But if it ever did, that would be a lithium minus ion. Again, it never happens. It just don't happen that way. If that was a chlorine, yes. But chlorine would have a lot more pluses there and they didn't want to bother drawing. It also had a lot more negatives in the outer shell. They didn't want to draw those. So they just did it the easy way and did that. Anytime you have an unbalanced number of electrons, excess electrons, negative ion. Deficit of electrons, positive ion. Never change your neutrons. I mean your protons. All right. Any questions on that? All right. Any of you ever dry clothes? In a clothes dryer? What is somewhat aggravating sometimes?
When it cuts off and then finish drying.
Okay, well that's aggravating too. But I mean when they're dry and you pull them out. Huh?
Static electricity.
Static electricity. Have you ever pulled them out and they're stuck together and you actually pull them apart and you hear that's static electricity? Because in the dryer they've been bumping into each other. Some have gained electrons, some have lost. One's positive, one's negative, they stick together. You have to literally pull them apart. Or when that skirt or pants leg sticks together or sticks other things to it, you call it static cleaning. That's static electricity. That's what we're talking about here. What we call that is electrostatic charge. Now, electro means what? What word do you almost see in that? Electron. Well, tron. Okay. Electron. Static means stationary. So what you've done, an electrostatic charge, a charge has gone over there and stayed. An electron's gone over there and stayed. Or left here and stayed. The stationary charge, static stationary charge, confined to an object. Okay? Now, what's even more irritating to me, have you ever opened a little pack of crackers, that foil, cellophane, whatever you call it, on it, and you open that, and it sticks to your hand. And you try to get it off, and it sticks. So you pull it off, and it sticks to that one. That's so aggravating. That's static electricity. Your stationary charge is confined to that object and will not let you go. Okay? Aggravating. What are the charging mechanisms? Well, in your dryer, that was friction. In the cellophane, you ripped apart bonds, and you had electrons exposed there. Okay? Or another one, contact with a charged object. Okay? Let's see if they have some illustrations of this. I don't think they do. Yeah, here's one. The gal's hair looks pretty good, doesn't it? Okay, now hair, sort of like fur, has positive and negative charges on it. It's neutral. The comb is neutral. Perfectly fine. And especially if this is a rubber comb. This does it really badly. Or something. But when you comb your hair, sort of like the amber, the electrons leave the hair and go on to the comb. That leaves the hair slightly positive charged. So she combs her hair and now it starts going crazy. Now when would this happen? When her hair is very clean, no oils on it, but also it's very dry. The hair is dry, the air is dry, everything's dry, and then it starts to do this. That really gets aggravating. Why did it do? The electrons left the hair, went to the comb, and now the hair, the individual hairs, which really look pretty good to begin with, now they're all slightly positively charged, so now they try to repel each other. So the hair stands out as far away from other hairs as it can, and she's far worse off than what you want to deal with. Now here's something you can do with the comb. Take it over here and rip up little bitty pieces of paper and hold the comb near it, and you'll see some of them jump up to the comb. Why? The comb is negatively charged and the paper is neutral, so it gets pulled to it. Now, Another thing that can happen is, okay, well, let's go back to this one. The piece of paper here, the first one that jumps up there, it now becomes charged, and it pulls the next one up. So you can have a stream of those little pieces of paper. Now, hopefully y'all don't have this, but we do in our old house. Ever have or see a cobweb? Now, is that actually a web? Do you have a spider named Cobb that made that web? No. What that cobweb is made up of individual, lots and lots of individual, guess what? Dust particles. The dust particles are so tiny that you've had broken bonds there. Some of them are positive, some of them are negative, some are positive. So what they happen, they link together and form what looks like a web, but if you ever touch it, it just falls apart as dust. Okay? Because that's all it was. These are contact with another charged particle, and you get a string of them. Now, polarization is what happens when I hold that comb near the piece of paper, but it doesn't quite touch it, but the paper starts lifting to it. Okay? Now, this is very hard to do, but it can be done. And as it lifts to it, the comb, remember, is negatively charged. Okay? So it pulls the electron, pushes the electrons that are in that little scrap of paper far away, leaving positive charges here. So that's what comes up here. Then the negative electrons are down here. The paper is still neutral, but they're just redistributed. That's what we mean here. Reorientation of the charges without changing the net charge. So now the negatives are down here. They pick up on the next piece, the next piece. You can actually have a chain just like your cobwebs, but now they're little pieces of paper. Okay? That's polarization. Let's see if they have a picture for that. Yeah, here we go. Now, here's the comb, negatively charged. You hold it near. Now, never this pretty piece of paper like that. It's ripped and torn and stuff like that. Little bitty pieces. It never pick up a big heavy piece like this. But what happens, you you hold it near, and without touching it, if you touch it, now you charge it. Some of the electrons go here. But if you don't quite touch it, it pushes the electrons away, pulling the positive charges toward it. So now you have polarization. You have more positive charge up here, less down here. The paper is still neutral, but you have polarized the paper, giving it poles, positive pole and a negative. But it's still technically neutral. All right. Let me keep up with where we are here. We're now on page 143, bottom of the right-hand column. Okay? Electrical conductors and insulators. Your electrical conductors, to be a good conductor, you have to have some electrons that are free to move throughout the material. A lot of materials do not have that. Okay? If you add more charge to it, it dissipates because the electrons are free to move. Now, most of your metals live down here, in this part of your periodic table. There you'll find titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, molybdenum. Only going to say one. Palladium, maybe you've heard of. Silver, cadmium, indium, you probably haven't heard of. Tin, you've heard of tin. Okay. Tungsten, iridium, you probably haven't heard of. Gold, you've heard of. I've never had much. Okay. Mercury, titanium. Here, and there's lead over here, all metals. Okay. In this part. Now, why are they in this part? Because these have, you'll learn later, chapter 8, these have the electrons a bit further from the nucleus and the electrons are pretty free to leave one atom and go to the other. Okay? And not just go to an atom, just flow around. Sort of like a herd of wild horses. They just take off and go wherever they want to. Within the meadow, okay? Within the prairie or whatever. So, kind of like teenagers. No, I wouldn't say that, would I? Okay. Now, graphite, carbon. Now, carbon just happens not to be a metal, very definitely a non-metal. It's over here. But it's right next to the semiconductors, which we'll be talking about later. The carbon happens to be a good conductor. Why? Because it has 4 unpaired electrons. So it's real easy for electrons to move around between those 4 unpaired electrons. Silicon also has that. It becomes a semiconductor. So carbon, graphite carbon anyway, is a good conductor. Diamond carbon is not. All those electrons are tied up in bonds. But graphite carbon, there are free electrons. So what is electrical insulator? Where you don't have those free electrons. The electron motions are restricted, like in diamond. The diamond is going to bond all those carbons together, electrons together, not going to leave any free, so they're not going to conduct electricity. Both diamond and graphite are pure carbon. This is 2-dimensional bonds, meaning it has free electrons exposed. These, all the bonds are 3-dimensional, and they're all stuck together. Okay? So the added charges tend to remain on the object, on the surface, doesn't dissipate. Glass, wood, these are not great examples. Diamond, ceramics, all those are generally good insulators. Rubber. Okay. Then you have your semiconductors. Sometimes they're decent conductors, other times they're terrible conductors that are good insulators. These conduct or insulate depending on the circumstance. It could be temperature, it could be orientation, it could be other things, and your applications of this are your computer chips. Okay? Solar cells. These are all made of semiconductors, and the semiconductors, one I mentioned first was silicon. Not the best one, but it's one. What did they name the valley where all these chips are made? Silicon Valley. Not because they have silicon there, but because of the semiconductor industry that's there. Okay. That's the bottom of page 143 over to the top first column of 144. Now, electric charges. We've talked about in general what carries a charge. Electrons. Protons also have charge, but they don't take it anywhere. They stay in the nucleus. So you have the electrons. And that's what's moving. But electrons are incredibly tiny, okay? And it takes an awful lot of them for you to, if you had an electron in your hand, you wouldn't feel it. It wouldn't shock you. It's just too little of a charge. You have to have literally gazillions of electrons to get enough to shock you. So we have to have a macroscopic unit to measure charge. Electron charge, way too small. That's submicroscopic. So the macroscopic unit is a coulomb. Named after, notice it's a capital C, named after Charles Coulomb, a French physicist who lived about the same time, I believe, as Benjamin Franklin. And if you remember Benjamin Franklin, he did some experiments with electricity. And he was also an ambassador in France. I bet you they got together. I don't know that for a fact, but I bet you they did. Okay? A 1 coulomb of charge is equivalent to the charge of 6.24 times 10 to the 18 electrons. Now, what would that be? That would be 6, 240, 240, 000, 000, 000, 000, 000, 000 electrons. That many. I don't know what the unit for 10 to the 18 is. That's way bigger than anything I know. And that is the metric unit of charge. Metric, SI unit of charge. What do we use in the U.S. customary system? Coulombs. No, we may use coulombs because coulombs came in along after the metric system was put together, before anyone knew about them in the English system. So when they came up with the units, everybody used them. Whether they're British, American, French, international, it doesn't matter. Everybody uses coulomb. Now, the electron charge is actually your fundamental charge. You cannot have a charge smaller than an electron charge. Okay? Even Mendez is bigger than electron charge. Okay. All right, we're slowly getting there. We know Frank won't be here, and Latricia probably won't because her new job has her tied up. Okay? So, electron charge is fundamental. Smallest charge seen in nature. You cannot get a fraction of an electron charge. You can't. That's the smallest seen in nature. Quantity of charge and the number of electrons, that's a weird bullet point, isn't it? Okay? That's what we're getting here. 1 coulomb of charge is that many electrons. Okay? Now, I think what they're going to show here is the formula that you get it. The symbol, and remember what I said this last chapter, capital Q in the last chapter was your unit as your parameter for what was capital Q. We used it in lab. What did that represent? Capital Q. Measured in calories. Are you cool? Heat. Q in chapter 4, capital Q was heat. Little q in chapter 6 is charge, is coulomb. The quantity of charge measured in coulombs. Now, what this was trying to say, the quantity of charge and the number of electrons are related to each other, because E is your single electron charge, and if you have this many, 6.24 times 10 to the 18 electrons, then you have 1 coulomb of charge. But if you have fewer than that, you have a fraction of a coulomb. If you have more than that, you have multiple coulombs. So that's what they mean by this. Without that, it didn't make a lot of sense. Okay? Here is how much a single electron charge is. It's the number of coulombs divided by the number. You just divide both sides by n. So if you had 1 coulomb, and you know that is equivalent to 6.24 times 10 to the 18 electrons, that's the number of electrons, that should be plural there, and you do that on your calculator, 1 divided by this, or you can just take this number and hit the reciprocal key, which is 1 over x key or x to the minus 1 key. Either one, you'll get this number. And this is the number of coulombs in a single electron. 1.60 times 10 to the minus 19 coulombs. If you really want to know what that is, you probably don't, but I'll tell you anyway. It's 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 0.00000000016. Okay, that's an incredibly small number. That's how many coulombs are in one electron. Okay, we never measure individual electrons. We measure so much charge in coulombs. Now, let's do example 6.1. Okay? Combing your hair on a day with low humidity, we don't have many of those in the southeast, results in a comb with a negative charge on the order of 1.00 times 10 to the minus 8 coulombs. Capital C coulombs. What's that a measure of? Q. That's your little q. Okay? Now, how many electrons were transferred from your hair to the comb to produce that charge? What would represent the number of electrons? What symbol? We just added in the last formula. This one right here. Which is the number of electrons? N. Okay? So we're looking for N. That's the unknown. How many electrons were transferred from your hair to the comb? So, if you're looking for N, what you do is go back to this formula here, and rather than solving for E or for Q, let's solve for N. What would N be? N is equal to, how would you solve for N? Isolate the N. Divide it by E. Okay? So it would be Q over E. And E is the electric charge of a single electron. That's it right there. Okay? So, come back to the current slide. N is equal to Q over E. I like to put E minus. I don't usually put a 1 with it. But E minus, which indicates it's an electron. Because E can be many things. Exponential notation, a lot of things it could be. So I put a minus with it. But the book doesn't, so you don't have to. Okay, so this would be 1.00 times 10 to the minus 8 coulombs divided by your electron charge, which was 1.60 times 10 to the what? Minus 19 coulombs per electron. Okay? Okay? Now, if you divide these, you'll notice the coulombs cancel out, and you're left with 1 over electron, and that would give you how many electrons. So, anyone got a calculator? Now, you need to know how to use scientific notation. We've done it before. Remember, you do 1, you don't have to put the 0.00. EE or EXP, then you're minus 8. And it's either the minus sign in parentheses, never the subtraction minus. The minus sign in parentheses. If you don't have that, look for a plus minus key. If you have the plus minus key, press the 8 first, then the plus minus key. If you have the minus key in parentheses, use that first and then the 8. Divided by 1.6, you don't have to do the extra 0, EE or EXP minus 19, however you do that. Negative 19 or 19 plus minus, however you do it. Equal. What do you get? Anyone? Something close to 6. 6.25 times 10 to the, how much? 10th. Positive 10 electrons. What? That's 62.5 trillion electrons you rubbed off your hair onto the comb. Didn't you feel a lot lighter when you lost that many electrons? No. Electrons are so incredibly non-massive, you never noticed a thing. That seems like an awful lot of them, doesn't it? 62.5 trillion electrons. Okay. Now, that was example 6.1. So let's clear that off the slide because I'm on the electrostatic forces slide. Does anyone need this any longer? Okay, everybody see how to do that with your calculators. Okay, all right. So, electrostatic forces. It follows, guess whose? Coulomb's law. Okay? And here is Coulomb's law. The electrostatic force, that's what F is, electrostatic force, is proportional to the product of the charges directly proportional to the product of the charges, inversely proportional to the distance between them, squared, inverse squared law, okay? Now, it does have a proportionality constant, that's K. This is sometimes called the electrostatic constant, sometimes called Coulomb's constant, and that is 9.00 times 10 to the 9 Newton meter squared per Coulomb squared. You see why that unit has to be that way. You need the Newton to make force in newtons. You need the meter squared up here to divide out the meter squared down there. You need the Coulomb squared down here to divide out the Coulomb squared up here. That leaves you in newtons. Okay. Now, I know that all of you, when you looked at that, said, oh, isn't that a lot like the equation for the force due to gravity? Yeah, I know all of you were thinking that, or most of you were anyway, right? Okay, maybe a few of you weren't. But the force due to gravity, the universal gravitational formula, this is force due to gravity, this is electrostatic force. I'll just put that way. That was gee whiz, m1, m2 divided by d squared. Oh, that is similar, isn't it? Now, of course, there's some pretty big differences. Masses don't really compare to charges very well. Distances compare to distances. But these are somewhat similar in form. But take a look at the difference. Remember that universal gravitational constant? If you don't remember it, you can go to the front of your book. I hope they put it in here. Somewhere near the front of the book. If not, okay, turn one page. Turn another page. Nope, turn one more page. Okay, turn to the back of the book. I thought I found it in there somewhere. Goodness, I have a lot of blank pages. Okay, not that. Turn one more page. One that says conversion factors. Yes, there it is. What page is that? Does that have a number? 204 in your little skinny books. You see Fiscal's constants in the right-hand column, midway, and you find gravitational law constant, capital G, 6.67 times 10 to the what? Minus 11. And this would be Newton, meter squared, same numerator thing, per kilogram squared. Different denominator. Okay, near the back of your book, what page you say it was? Diamond?
204.
204, very back of the book, yeah. Very back. There's a bunch of blank pages in the back right before you get to them. Page 204. See it? Okay. Now look at the difference between these. K, 9.00 times 10 to the positive 9. G, 6.67 times 10 to the minus 11. This would be 9 trillion. No, I'm sorry. 9 billion. I said it wrong before. 9 billion. This would be something like 0.06 billionth, okay, with a TH on it. Incredibly different. So the K versus G indicates that gravity is weaker than electrostatic forces. But we just imagined that we saw that, didn't we? When I had the comb, the imaginary comb that I brushed my imaginary hair with, and it was lifting imaginary pieces of paper, electrostatic force was greater than force due to gravity. It overcame that and lifted it up, remember? You mentioned all that, didn't you? Yeah. Okay. There indicates how strong electrostatic forces are. Here's the big difference, though. Electrostatic forces don't travel very long distances. Very short distances, whereas gravitational forces go across the universe, or at least across the galaxy. Okay? So way, way longer range. All right, and here's where they show that. Let me get this off the page. Here is your force due to gravity, is universal gravitational constant, that number. And here they got something wrong. Do you see that? It's G M1 M2 divided by D squared. That part's the same. It's just masses rather than charges. But they should be M squared here, not M. And in your text, trying to see if they have that. Well, I don't see it in your text. I thought it was in there, but I don't see it now. Okay. But on the slide here, that should be M squared. Okay. All right, any questions on that? Electrostatic forces. And here's the ratio of K to G, even though it's not a very reasonable thing because they have completely different units. 9.00 times 10 to the 9th divided by 6.67 times 10 to the minus 11. You punch this in on your calculator, you'll see this comes up to 1.4 times 10 to the positive 20. That's, whoa, incredibly more powerful. K is many, 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 many times larger than G. All right. Now we get to force fields. Oh, wait. We have example 6.2. Let's go back and do example 6.2. Let's erase what we got here. Electrons carry a negative electric charge and revolve around the nucleus of an atom, which carries a positive electric charge from a proton. The electron is held in orbit by the force of the electrical attraction at a typical distance of 1 times 10 to the minus 10 meter. So what would that be in our formula here? Not that one, this one. That's your D, the distance between them. So we have D is equal to 1.00 times 10 to the minus 10, right? Yeah, minus 10 meters. Okay? What is the force of electrical attraction between the electron and the proton? Okay? Force for electrical attraction, that goes back to this too. Where was it? Oh yeah, I must have hit that. Here we go, right there. That's this. So this will be K, which we know. So let's write it here. F, that's what they're asking for. What is the force? Okay, electrical attraction is equal to 9.00, that's your K, times 10 to the 9th Newton meter squared per Coulomb squared. That's the K part. Times, now what's the charge on an electron? Okay, we have to go back a couple more slides. There it is. 1.60 times 10 to the minus 19 coulombs per electron. 1.60 times 10 to the minus 19 Newton meter squared per Coulomb squared. No, that was that one. This is Coulomb, sorry. Duh. Just coulombs. But what's the proton? It's also 1.60 times 10 to the minus 19 coulombs. divided by your distance, which is 1.00 times 10 to the minus 10th meters squared, because you have to square that one. So you got a lot of exponents to do here. So let's see if we can get them right. Okay? If you got your calculator, start pumping here. 9, you don't need the 0.00s. 9 EE or EXP 9 times 1.6 EE or EXP minus 19, however you enter that on your device. And what you could do, I wish I would have said it sooner. Okay, times 1.6 EE or EXP minus 19 again, divided by, this time open parentheses, 1 EE or EXP minus 10, close parentheses, squared. Okay? Now, let's see what happens to the units. Here's Coulomb squared, that's Coulomb times Coulomb, they go out. Here's meter squared, here's your meter squared, that goes out. You're left with newtons. How many newtons did you wind up with?
2.3 times.
Say again?
2.3 times 10 to the negative
2.3, is that what you said?
8 times 10 to the negative 8.
10 to the minus 8. And that would be newtons. That's what unit we had. That sounds like a pretty small number, isn't it? Unless you realize that force is mass times acceleration. The mass of that electron is incredibly tiny. That would give it an acceleration that was absolutely incredibly large. Okay? And they did 2.30 because you have 3 significant digits. Times 10 to the minus 8 newtons. Very good. The electrical force of attraction between electron and proton. All right. All right, now let's move to force fields, which is on page 145. How do forces act through space? How does gravity act through space? Pretty amazing, isn't it? There's no connection there. How does it act through space? Well, there's nothing that links it. So charges are surrounded by what we call electric fields. These electric fields are vector fields, meaning they have directions. The fields and the charges are inseparable. If you have a charge here, you got a field around it. If you have a charge over here, you got a field around it. You cannot have a charge without a field, not an electric field. You can't have an electric field unless you have a charge somewhere. You have a gravitational field, but you got to have a mass. Okay? So fields act on other charges. Okay? And the direction of the field is the motion, and here's what we assume, the motion that a positive test charge would take if it was in that field. So let's say we have a charge up here. Okay, you tell me whether you want it to be a positive charge or negative charge. Negative charge up here. So here we bring in a small test, always positive, test charge. Which way is it going to take off? Toward that or away from? Toward it, because it's positive charges. So therefore, this negative charge up here, the field lines are always pointing toward it from every direction. Because any player you put a positive test charge is going to go toward it. Now what if this was a positive charge you had here? And bring in a small positive test charge. Which way is it going to go? What will it feel? It goes away. So the field lines always point away from a positive charge, always point toward a negative charge. Okay? The direction of the field is the motion a positive test charge would take if it was there. It's visualized by lines of force. There aren't really any lines there, we just visualize it that way. The same idea applied to gravity, to magnetism, to all sorts of field charges. Okay? The difference between gravity and this Gravity is always attractive, never repulsive. Magnetism, though, acts more like electric. So here's what I was just saying. If you had a negative charge here, that's what Diamond wanted, a negative charge here. You put a small positive test charge, it's going this way, so your field lines always are pointing toward your negative charge. However, if you have a positive charge here, your test charge is here, that's pushing it away, so your field lines around positive charges are always away from the positive charge. Field lines point away from positive charges, they point toward negative charges. Always. Okay. Well, there's some slides missing here because I keep pressing buttons. Now, this is what would happen if you brought two positive charges near each other. Okay, because the field lines are pointing away from both of them. Field lines never cross, by the way. Electric field lines, gravitational field lines, magnetic field lines never cross. So if they're pointing away from each other, they're pushing each other away. That's why light poles repel. Okay? Because they're bending those field lines, they're acting like leaf springs in a truck and pushing away. Okay? They're trying to go back to their normal state all the way around, so they push these charges away from each other. Okay? That would happen with light charges. Now this shows, I think, a positive here and a positive there, right? I can't read it. Yeah, in parentheses. What if they were both negative? What would be the difference in this picture? Okay. The lines would be the same, all the arrows would be pointing inward, not outward. That would be the only difference, but they would still be bending away because they're trying to get away from each other because they're going in the same direction. Okay? But what if this was a positive and that was a negative? These are pointing away from the positive toward the negative. Hey, link up here. We're heading in the same direction. So they do link together. The strongest is here, weaker up here. You even get some way out there, but not much. But the strongest attraction is right there. Bring them toward each other. Okay. That's force fields or field lines, however you want to say it. Okay? Now, next concept, and this is a really important concept, that of electric potential. We're going to come back to this later, but here, hang on to it because it is pretty important. Forces are vector quantities. Fields are vector quantities, but electric potential is a scalar field, which sort of is a weird way to say it, associated with potential energy. Okay? So there's no motion, no direction involved in this. It's just a scalar. The unit for electric potential is volts. Pretty important. Why is that capitalized? Any ideas?
Lowercase v is velocity.
Little v would be velocity, you're right, but that would be a parameter. This is a unit. We also use capital V for the parameter too. But why would the unit be capitalized? Named after Alessandro Volta, okay, from Lake Como, Italy. I was fortunate, lucky, my wife goes to professional meetings quite regularly, but sometimes they happen to fall on one of the weeks I'm out of school. And she was going to Lake Como, Italy, one summer, between spring and summer or summer and fall, I don't remember which it was, but I got to go along. We took our niece with us. And while she was busy at meetings, the niece and I went out, saw Lake Como, a beautiful area, rode the boat on the lake. We took the tram over to Switzerland and got some chocolate. It was just great. But while we were walking along there, there's a beautiful little monument sort of thing there. We said, well, what is that? Let's walk and see. And it was, I didn't realize Volta came from Lake Como, Italy. That's why I know that, because this was a monument to him and it shows some of the early work that he did with voltages. Okay? And name the unit after. It's related to the work involved with persisting charges. So if we had this negative charge up here, remember that's what diamond wanted here, and we were going to bring another negative charge, we would have to do work to get it to go close to this one. Okay? If it was a positive charge, we would have to do work to hold it back to keep it from slamming into it. Okay? So we'd have to do work. It's related to the work involved in positioning charges. The potential difference, that's what we're talking about here, potential difference, volts, is important in producing forces and moving charges. That's what moves charges, potential difference. It's analogous to moving masses in a gravitational field. I lift the book higher and higher. I'm doing work against the book. The book's being pulled downward by the gravitational field. I'm doing work against it. That's analogous to your potential difference here. And by the way, a volt is a energy per unit charge, or work per unit charge. Joules per coulomb. That's what a volt is, by the way. So, here's exactly what I said. If it took 1 joule of energy to bring this 1 coulomb of charge in close to the stationary 1 coulomb of charge, if it took 1 joule of energy, the potential difference between those is 1 volt. That's what a volt is. Joules per coulomb. Joule of work per coulomb of charge. And here's the formula. The volt, the electric potential difference, and by the way, the parameter, and we use capital V here, is voltage, but we use capital V because little v would be velocity. So capital V here, don't confuse it with a unit capital V, same capital V, but this is potential difference, the parameter is work per charge. If you use units, that would be voltage is equal to joules per coulomb. Now, we get to electric current. Earlier with electrostatics, we had static charge, not moving charge, okay, stationary. Now we're going to then the charges were more or less fixed in place, on the piece of paper, on the comb, on your hair, wherever they were. But now we're going to allow charges to move. That's why we needed the conductors to connect them. So what we talk, electric current is a flow of charge. Flow of charge. Now, why do you have a flow of charge? Because you have a potential difference of voltage that is the energy per charge, okay? And that gives you the flow. So electric circuit are structures designed to localize and utilize those currents, okay? That's what your circuit is. Structures designed to localize and utilize, I'd prefer to use there, currents. So here's an example of an electric, and this, by the way, is 6.2 electric, well, in here it's saying electric circuit. In the book it's electric current, okay? Oh, that was electric current. The next page is electric circuit, okay? Here's the structure. Said here, the structure is designed to localize and utilize currents. Here's the structure. You have to have a voltage source, an energy source, to give the energy to those coulombs of charge. That's your energy input necessary for continuing flow. If you don't have a potential difference, you're not going to have current flow. Gotta have it. You have to have a circuit element. That's whatever's going to use that energy. That could be a heater, it could be a light bulb, it could be a paddle wheel, it could be anything like that. That's your circuit element that uses the energy. It doesn't use the current. It uses the energy from those charges. The voltage doesn't produce current. Well, it sort of does. It gives the energy to the charges. Okay. Now, we have two current flow conventions. Okay? The one that makes the most sense physically is that the current always flows from high potential to low potential. Remember, the heat pumps and those kind of things always flow from high temperature to low temperature. That's how everything in physics is. High concentration to low concentration. Always goes from high to low. Okay? So that's what we call conventional current. We have a problem though, Houston. Our charges are negative, the electrons. So the electron flow is in the opposite direction. It goes from negative to positive because you have excess electrons on the negative, deficit on the positive, so it goes the other way. But don't worry about that. It really isn't important what charges are actually moving. The important thing is what energy they have. Voltage, energy per unit charge. Now here's the water pump analogy. I'm trying to do this fast because we're really into lab time right now. And we do need to get some understanding of current circuits before we can do the lab. So let's try to get this done quickly. So the structure here, here's your battery, so to speak, what it looks like. It gives energy to the charges. It doesn't create charge. It doesn't destroy charge. It gives energy to the charge. Okay? Now, the charges move around through the conducting wire. There's the third circuit element. You have to have a voltage source. You have to have an element. The third thing, you have to have a pathway, a wire. Okay? Something to conduct the electricity. In the battery, it's a fluid. You have both positive and negative charges moving in here. The positive charges, the ions are moving this way, negative ions moving that way. Okay. So your conducting wire, here's where you have a voltage drop because you're using the energy that the battery supplies. You're not using up the charge. The same charge leaves that came in, it's just it doesn't have as much energy. That's where the work is done, to produce heat and light. Okay? And then it gets back to the battery, pumps up the charge again, goes again, and again, and again. Now here's the water pump analogy. The pump is like the battery. It gives energy to the water by pumping it up here. It has higher potential energy here than it did down here. So that gives energy to the water, but then the water flows through the tube, hits the paddle wheel. This is like the light bulb. The tube is like the wire, okay? And the high energy water turns the tube. It uses the energy of the falling water, goes back down here, pumps it up again. The battery, the wire, the light bulb, the wire, okay? That's your analogy. Now, they don't always work completely. What if you cut the tube here? Water spills everywhere. If you cut the wire here, what happens? It stops. Nothing goes through. So you can't use the analogy forever, but it does hit the big points there. Okay. Now, here's where the problem arises. Our conventional current goes from high potential to low potential. That's where everything in physics does. That's what we say where a positive charge would go if it was a positive charge. Of course, it's not a positive charge. Most of the motion is electrons, and they're negatively charges, so they move in the opposite direction. So you have the conventional current this way, the electron current that way. It doesn't matter, because really what's important is the field, not the actual flow. The field. And the field is high potential to low potential. All right. Historically, the nature of the electric fluid was unknown. We didn't know what it was, so they gave it plus and minus. In fact, I've heard that Benjamin Franklin was responsible for that. If he had only named the electron positive, not negative, then everything would work fine. But he named them the other way, so that gives us all this problem. All right. The current was thought to be the flow of positive charge. Reality is much more complicated depending on the material. Like I said, in the battery, You got positive and negative charges going in opposite directions. So how do you say what the flow is there? But in the metals, it's usually electrons that are moving. They're not moving as fast as the field moves. Nowhere close to it. So we do have that little discrepancy there. You'll see it on your lab too. Okay, the current mechanism. Let me just look ahead a little bit. You know, I think we can go with what we've got now. We will start next time with current mechanisms. Okay? Now, there may be some things I have to tell you in the lab. I don't think so. But let me see if I can find current mechanisms. Whoa. It's somewhere right about here. Page 149. I'm sorry, folks. Okay. All right. Before you go, let me go on and give you the lab. Now, this is one of the books labs, the lab manual labs. But guess what? This is one of the few ones you'll have all term. Maybe not the only one, but one of the few ones. Well, your working power lab, that was one from there that you didn't have a graph. This one you don't have a graph. Enjoy. Okay? I know y'all love your graph stuff. Here is the electric current circuit lab. Okay? So if you'll take one and pass 3.
$253.
Second will be and 253. Yeah. Now, I haven't gotten set up because I had a student in for advising. I only had 15 minutes. They took up the entire time. So I'm going to go get the request. So maybe that's a couple drops. And let me get 4 of them. Huh? Wait a minute. I gave someone too many, I think. Oh no, I already gave. That's right. I already gave 1, 2. All right, it's going to take me several minutes to get there. And when I get there, I'm probably going to need a few strong bodies and weak minds to help me move some equipment. Okay? Okay, we got it. Okay. I like that. Okay. Take a break. It's going to take me a little while to get down. I know you've been reading your lab because you were very anxious to learn it, okay? Just a few words about electric circuit. It's a conducting path for an electric current. Okay, we're going to be producing some currents. Current is a flow of charge, stuff we had in the text today. Now, we're not doing procedure number 1 exactly like it's written here. What I want you to do for procedure number 1, on your page 180, in the rectangle on the top right corner of the page, I want you to sketch, forget about 1 battery, 1 bulb, and 1 wire. I want you to make a sketch just like number 1 below that. You can leave off the switch if you want to. We're not going to use the switch, so you can leave that off if you want to. But draw the battery. By the way, wait, I should have done this first. Wait a minute. Okay? Notice here on page 179, in that figure 20.1, the battery is listed there. Now, technically, if they were being really special about it, that would be a 3-cell battery. A short line is the negative side, long line positive, short positive, negative, long positive. So that would be a battery. The positive is always on the outermost long line. The negative is the outermost short line. Okay? That's your battery. We're not going to be dealing with grounds here, but our bulbs are going to look like the one that says bulb there. It's a resistor, which we haven't talked about yet, inside of a circle. Just a plain old resistance is just the zigged lines, like you see inside the bulb. Okay? Open switch we're not going to deal with, so you can leave that off if you want to. That's all you need right now. So, if you draw number 1, maybe without the switch, in the rectangle above, draw your battery just like it shows here, a long side, short side, and then draw your bulb with a jagged line in the middle and a circle around it. That's all you need. Okay?
You want all 3 of those in that square.
Yeah, just draw number 1, just number 1, inside there. Just number 1.
You were just saying, like, this is the whole.
And you can leave off the switch if you want to. You can just draw a straight line through that. Okay, now, see, Diamond already has her drawn. If you want to, you can put the plus and minus poles in the battery, but you don't have to. Okay, everybody got it drawn? Looking good, folks. So, now, what I want you to draw, and we had a figure in the text on the slide set, very similar to that drawing you just did. And I want you to put with arrows which way conventional current would be flowing and which way electron current would be flowing. If you still have your book with you, might be a good idea to look for that drawing. Okay? But does anyone remember what the conventional current, which way it flows? From positive to negative. So wherever you put your positive, conventional current would be leaving there, the arrow pointing in whatever direction will ultimately get back to the negative. What would be the direction of your electron current? Negative to positive. So draw that arrow the other way. But be sure you label your arrows. Okay? Which one's conventional, which one's electron. Okay? That's your procedure 1. Is draw your conventional current arrow and a electron current arrow. Identify both arrows. All right. Now, I know all of you can't see the bulb that I have in my hand, but you probably have seen a bulb before. Okay? Now, the bulb has a metal tip at the end, but it's separated from the rest of the bulb by plastic. The metal is what kind of material? Conductor. What is the plastic material? Insulator. Okay? Then you see there's metal around here too, which is a second conductor. Very good. Now you can imagine looking in the bulb. There's a wire going up and another wire going up. Okay? If you look at the figure 20.2 of a bulb there. Okay? You see the tip down there, which is a conductor. You see it separated by a dark area, which is an insulator. Okay? And then the jagged edges of the bulb, that one screws in, this one plugs in. Okay? That's also metal. Okay? That would be a conductor. Now, you see here is the filament, but you got these two things dangling there, not connected to anything. In order to make that flash, bulb light, the light come on, where would you have to make connections? Yet, one each to a different conductor. Now, is the one side or the other side of this different conductors? No, that's one conductor. What's the other conductor? The tip. So one of those goes to the jagged side there, the other goes to the metal tip at the bottom. Make sense? Otherwise, light doesn't come on. You have to make that connection. Everybody follow what I'm saying? Excellent. Okay. You understand? Okay, yeah. Draw, connect, complete the circuit. So, no. Just the ball. On the ball. 20.2. Excellent. Nothing. All right. I can't remember which one I stole this from.
It's literally just like a chocolate fries.
All right. So there you've completed number 2, procedure number 2. Now, we're ready to do procedure number 3. Now, yeah, I'm going to set up your circuit 1 for each team. I'll explain this to you as I go. Okay? The red wire, think of that as the plus side of your battery. This is a power supply. It produces DC current. But think of that. Now, why did I put it here? If you look at this, you can almost see the soldering in here. It's clearly soldered on this side. And it goes from there. They actually drew lines. It shows it goes from this point through the bulb and then to this point. So that's why I set it up in that direction. Not here to here, not here to here, not here to here. You know, this corner to that corner. Okay. All right.
I got this at TJ Maxx, but they sell it for like.
You can see sort of what the soldering was. And you can see the diagram here, it goes from this pin to that pin. That's okay, going through the line. Almost like but it was at the center. One of them. That there. And that here. Because you see where the soldering was? Through this. Out here, not here, and this diagram also shows that. Okay. Now set up the circuit for everybody. That is trash. Okay. That is your circuit number 1. 1 battery, 1 bulb, complete circuit. Right? Okay. Now, it says wire it this way. For each circuit, note if a single bulb lights dimly, brightly, or not at all. We'll get to that. And note when 2 bulbs are lit, if unscrewing or removing 1 bulb affects the other in any way. We'll record the data on and other observations on data table 20.1, which is your very last page, 183. So here's what we're going to do to start. Okay? This is circuit 1. I've got it here. Now on your power supplies, your boxes here, there's a red button upper right. When you press that, you should see the light come on. The meter come on. Okay? You got it? Okay. Now, what I want you to do is very slowly turn the knob here that's above those 2 wires until you get sort of a standard brightness for the bulb. Very slowly turn it until you get some sort of standard brightness for the bulb. Keep turning. Keep turning. See anything coming on?
Yeah, I saw something.
Oh, okay, there you go. All right. Okay, it looks like you have a drifter. Okay. Don't get it too bright. Just stand it right. That looks good. Notice what your voltage is. 4.1. Okay. I'm going to turn yours off for now because you're good. You don't got yours? Just sort of standard brightness. Maybe a little bright.
What's the observation from that? Yeah, how many volts was it?
4.1.
That looks fairly good. Okay, get the red light and turn it off. Leave it in place. What you got? Ooh, you're too bright. Cut down, cut down, cut down. Ooh, not too much. Yeah, a little brighter than that. A little brighter maybe. That's good. That's good. What you got?
3.5.
All right. All right. Now, I want you to look carefully, or, as soon as you finish, did you turn it off? You saw what your standard brightness was. If you need to remind yourself, turn it on again, look at it. That is your standard brightness. You're going to be comparing everything to that brightness. That's your standard brightness. Okay? Now, under your observations, and maybe under question number 1, results number 1, I want you to record what your standard voltage was. And it was different for different groups. So record what that was. On page 183 under circuit 1, observations, and maybe on page 181, results number 1. Okay? Just record what your standard voltage was to give you the standard brightness. Okay? Everybody got it? All right. Now comes the part where you got to do something else. You need to... Okay. Okay, pay attention now, folks. Okay, you've got some wires over here to the side. You can either use white, red, green, whatever you got. And you've got another bulb over here. Okay? Now, what you need to do is to put these two bulbs, number 2, now this is a new word for you. We haven't gotten to it in the text. These two bulbs are in series. What does that mean? Yes. Okay, these two are in series because the current flows through both bulbs. So they're in one circuit. Okay? So basically what you do, you can use pins here and connect that one to, this is a real cheap way to do it, and then you're running out of spring over it. Okay? So let me see how you set up your series circuit. How are y'all doing? Oh, that's nice. Okay? Now, turn off your thing for just a minute. I'm going to explain something else to you. Okay? Turn them off. Okay. I want you to notice one other thing here. Okay? When you have a single pair of lines, one short, one long, that's going to be your standard battery. If you have a double set of lines, like you have for 3 and 4 and 6 and 8, that doesn't mean double the voltage. That means increase the voltage. Just enough so you can see what's happening. Don't ever exceed doubling the voltage. At least one time you may have to double it, but most of the time you're going to stay below it. So this one is same voltage as before. That's why I had you turn it off, so when you turn it back on, you'll be on that same voltage. Okay? Now, here are what you're going to write down. Everything you're going to do for right now is going to be on this last page. Okay? You put one thing on the previous paper, everything now is going to go here. And by the way, you can put down on circuit 1, observation, you put your voltage there, right? Also put standard brightness. Just to remind yourself, that's your standard brightness. Okay? And you remember how it looked too, right? Now, what I want you to do, this is 2 bulbs in series with the same voltage. Turn on your device, and here, not yet, but here's the 2 things you're going to write down. Okay? Number 1, what's the brightness of your bulbs? Is it dimmer, standard, or brighter? One of those 3. Actually, on one of them you may have a 4th one. No, not at all. It may not come on. Okay? But this is usually going to be dimmer, standard, or brighter. Okay? The second thing you'll do is what happens when you remove one bulb. All you do is just pick it up, take it out, and see what happens. Okay? So first thing you do, turn on your voltage exactly like it was before, and look at your bulbs, the brightness. Are they dimmer, brighter, or standard?
Turn it off before you do that? Turn it off before you do that.
Yeah, no. Oh, when you pull it out, you need
Okay.
it's not going to shine.
Okay,
Okay. What are they? Dimmer, brighter, or standard? Dimmer. Okay, everybody got it?
Yes.
Pull out one bulb. What happens to the other bulbs? It what?
Turns off.
It turns off. Okay? So those are the 2 things you're going to record in every block. Is it dimmer, brighter, or standard? And if you had 2 bulbs, what happens when you remove one? Okay? All right. Have you got number 2 done already?
Yes.
All right. This time, go back to your number 1 setup, as you had it in number 1. Number 1 setup. Yeah, take out the second one. Yeah, take it out. We're going to do it. Okay. The only reason I turn things off is so we don't burn out the bulbs. We only have a limited number of bulbs. Okay, plug it in just like it was before. Okay? Now, this time when you turn it on, it's going to be on your standard voltage. What I want you to do is just increase the voltage ever so slightly and tell me whether the light is dimmer, brighter, or standard. Just turn it ever so slightly. Don't exceed double. What you think? It's getting, yours is jumping all over the place. Yeah, it's getting brighter. Okay, turn it off. Okay, and you only have one bulb there, so that's all you answer. What did y'all get?
Brighter.
Brighter? What did y'all get? Brighter. Turn it off. Say again? That's circuit 3. 2 batteries in series. We didn't use 2 in series, we just used increased battery. Increased voltage. 5.9. It wasn't quite double. I didn't want you to double because you'll blow the bulbs if you double. Okay. Everybody got circuit 3 done? There's only one bulb, so you don't have to answer anything for that. Now do circuit 4. Looks just like your circuit 2, only this time we will double your original voltage. This is the one and only time you really will double the original voltage. You know what your original voltage was, right? So double it. What? This yours is a drifter. Okay, that's close enough. Good enough. Okay? Okay. What would you say about the brightness?
It looks standard.
Standard? What happens if you remove a bulb?
Turns
stops.
The other one goes out, right? Or doesn't?
Yes.
Okay, turn it off then. Now, before you do anything else for circuit 5, take out a bulb so nothing blows. Okay? Well, you can leave it in. Leave it right like that. And turn it down back to your your standard voltage. So go back to your whatever you started with. Okay. Oh,
Yeah.
okay. You there? Okay. Then turn off your battery. Turn off the power supply. Red button. Would be at standard voltage. Okay. Now you got to set up circuit 5. It's going to take a little more work. Use your things. How do you set up number 5? 2 bulbs in parallel. Notice what's happening here. On the plus side of the battery, you got a wire going to each bulb. So you can leave your, okay, yeah, whatever. Yeah. Well, put your other thing in, yeah, somewhere, not too close.
Well, you got
Further away, further away. That will do. Okay,
So
now,
run this cord from here.
yes, from here to there.
Yeah.
So from the plus side, that needs to go to the plus side. Okay. You need that number somewhere. And then there's another negative and negative. Let me see. Well, you started okay, but you're going to need to use some wire here. Okay? And you need to do plus to plus and minus to minus. So you need 2 wires. That's what that's not connected. That's good. See what you got. Yeah, it works.
I'll do it if I have to, but I'm not complaining a lot.
Okay. Turn it on to your standard voltage.
No, the black one is.
Oh yeah. Huh?
It's a little dim.
What do you say?
Standard.
Looks like standard to
Take
me.
one out.
Huh?
Take one out.
Take one out. Oh, it stays on. Did y'all do that too?
Yeah, I think
Well, wait, are you? No, you're at 2.5. This is 50. I know. This one drifts like that. Oh, too much. Push that one. Well, it's sort of sometimes. Right when you want to. Okay, that's close. What you say? Standard? Okay, what happens if you take the bulb out? What did y'all do? Okay, what do you get the light? Good deal. Okay. What happened? Stayed on. Good deal. All right. Now let's see. Identical setup here. Identical setup. plug them back in. What you do is just increase the voltage. Don't double it, increase it. Just increase it. Only time we doubled it was when 2 in series you could do that. Just increase a little bit and see what happens with the brightness. Brighter? What happens if you remove a bulb? And the other stays? Okay, let's increase a little bit. Okay, what you get? Okay, what about the brightness? Brighter. Okay, remove the bulb. This is what number 6. What happens when you remove it? Stay. The one stayed on. Okay. That was number 6. Now, turn it off. Okay. Now, I don't want you necessarily to wire number 7 if we can talk through it without actually doing it. What is happening with number 7? One bulb is parallel with just a wire. What do you reckon is going to happen? Okay. That's why I don't want you to do it. Okay. Now, but the other thing would happen, that wire would get very hot and probably bubble the insulation. That's why I don't want you to do it. But what would happen to the light bulb? What? It would not come on. Why not? Exactly. All the current. Here's what I think of, folks. I say that current is a lot like students. Always follows the path of least resistance, don't you? Never mind, I didn't say that. That's not what I meant. Okay. Faculty is what I meant to say. Okay. Now, so the current goes through the straight wire and doesn't even bother going by the battery. There's too much resistance there. That's too much work to go through that. So it goes the other way, so the bulb never gets in enough current to even come on. Okay? So, on your number 7, notice what it says. Show with arrows how the current takes the path of least resistance. So if you want to draw that circuit here, you can. You've got room. Or if you want to, you don't have as much room, but you could draw it on page 180 under number 7 if you want to. Draw where the current goes and where the woozle wasn't. No, where it didn't go. You don't draw anything there. Okay, if you have any questions, I'm here to answer. What's that? Number 7. Right, if you want to. You've got more room there than you do on the other page. You could just do it on the other page if you want. Now, write what happens to the bulb. Be sure you write that in that block too. Wouldn't come on. Yeah. Perfect. Okay, excellent. You don't have to go the whole thing. It goes around the bulb, doesn't even perfect. Okay. Be sure you put what happens to the bulb. Doesn't light up.
So the arrows like sort of here?
No, do it through conventional.
I'm trying to figure out what we're drawing.
Okay, you're drawing where the current flows. That's so.
So the current will flow this way.
No,
It goes straight through.
Yeah, yeah, and it goes through here. It doesn't go through the ball. Yeah, it goes through that part. Because there's no resistance there, not much. Lots of resistance to the ball. Okay. Now, you tell me, look at circuit 8 and tell me which ones it's the most like. Say again? Which do you say? Yeah, but which one? 6 is the most, 8 is the most like? 6. Okay? Notice there are 2 bulbs in parallel. All you have is switches. We're not doing switches. So except for the switches, those are identical. So you don't have to redo it. Just write down what you did for 6. Yep. Okay. Now, you want to go back to the classroom or stay here? Stay here. Okay? What you're to do now, that was your page 183. You've used everything from page 179 and 180. Now let's go back to results on page 181. The results on 181, you've already written something down there for number 1. You wrote down the standard voltage you were using. Okay. But now it asks for this. Describe which bulbs had a normal brightness. Look at your table that you did back here and say which circuits had the normal brightness.
Normal brightness? So like
Normal brightness.
same as our
Standard brightness. Standard brightness.
4 o'clock.
Okay, whatever it was for you. You were supposed to be writing it down. Which had standard or normal brightness.
You write down the bulbs are at the standard brightness.
Say again.
I got 1,
Well, just 1.
1, 4, and 5. Yeah.
and I'm just putting the bulbs.
Okay. That's all you have to do for number 1 is the circuits that had normal brightness based on your table or chairs. Okay. Number 2, which circuits had bulbs that were dimmer than normal? Okay. What's the confusion?
Circuit 7.
Okay. Note the color has nothing to do with it. Okay. Describe which circuits had bulbs with normal brightness.
Did 7 count as well? Since it didn't turn on at all?
You can if you want.
7. No, that would equal 6. That's what Number 2, number 7 are the answers to number 2.
Okay. Now, notice number 2, though, has another statement after it. After you list which circuits, you just list the numbers of the circuits, then it says explain. So you need to explain why those bulbs were dimmer. What's that?
Didn't have enough voltage.
Okay. That's,
More low, same.
okay, yeah. Same voltage, more load, more resistance. We'll be covering this a lot better in the next class. Sorry we had to do this a little early. You didn't cut yourself, did you?
No, my pen started thinking.
You need another?
I might have put my pen where it didn't belong. Kept a couple black.
Now, actually, on number 2, there probably are 2 answers. Okay? If you put two answers down, there's different reasons why they were dimmer than normal. So do one for one and one for the other. Did y'all put two bulbs? Yeah. And they had different reasons.
So we put number 7, but it never eliminated.
Yeah, so that was dimmer. So if you want to put it there, you can. But that's a different reason. Now, I want to describe to you just quickly what you call that. Anyone know what that is when you had a path of least resistance? What you call that? Short circuit, because the current goes through the shortest path possible, the least resistance. Okay? So that was the reason for number 7. Now, what if you would have had a switch in there and the switch was open and you plugged it in? Nothing would happen there either. But what was that issue? We didn't have one like that, but what was that issue? It's an open circuit. So a short circuit and an open circuit, completely opposite. The short circuit has too much current flowing in another direction, in another part of the circuit, whereas an open circuit has no current flowing anywhere. Okay? And yet the results are the same. No lighted bulb. So you have to be careful when you have something that doesn't light when you think it should. You could have a short circuit, or you could have an open circuit, completely different, way different, opposites from each other. Okay, that's enough of that. Number 3, which circuits had bulbs that were brighter than normal? Okay, and then be sure you answer the explain too. Anytime there's explain, there needs to be an explanation right after it.
Yeah, I'm at home. Yeah, 36. And I'm number 15. I said 15 systems. They all have higher voltage.
In all of the increase.
With the same resistance as the standard. Now we haven't gotten that yet, but we'll see it later. Okay. But that'll do for now. Okay. Okay, y'all moved on to number 4? In which circuit did removing one bulb cause the other to go out? Answer which circuits first, but then you have to explain. Okay. Now, why did that happen? What's that? Yes, the circuit was broken because in a series circuit, every element is part of the circuit. When you remove one, it opens the circuit. Yeah. No place, yeah. No path for the current to take.
Yeah, that's right. Due to being a series, the removal of all circuit.
Y'all ready for number 5? Ready for 5? Yea or nay?
Yes, ready.
Okay. In which circuits did removing one bulb not affect the other? Look at your table and see.
I didn't really part it. I just said moving parallel old was source of some energy. I just can't remember it. Number 6. I don't know. I just can't remember.
Okay, that also has an explained by it, so you need to say why. Kind of a why did you come up with? Explain. Okay, but why did that keep one lit? You're right. All three of those are parallel.
We increased the circuit as well.
You what?
We increased the circuit.
Not increase the circuit. Say again?
On number 5, it had its own power and ground.
I can't hear.
On number 5, the reason the bulb stayed lit is because it has its own power and ground as part of a different circuit.
Okay, you got it. The key there was there was still a pathway all the way around. Whereas in a series circuit, you remove one, you've broken the path. You broke the circuit, you opened the circuit. Y'all use those terms. But when you remove one from a parallel, there was still a pathway that it could get back to the battery. Okay? That's what parallel circuits do. Now, this is something we talked about in class. Well, I'll let y'all finish writing. Everybody finished with 5?
Yes.
Okay. Number 6. We said this in class. Describe the general requirements for any circuit to function. You have what?
Source, path, and load.
Okay, sounded good. What was the first thing you said?
Source,
But-
path, and load.
Excellent, excellent. What do you mean by source? Potential difference. Okay? A voltage supply, whatever you want to call it. Pathway is your wire or the circuit. Yeah, path is a great way to describe it. And then the load, you need something to use that energy. Yeah, that's your bulb. Now you need to answer number 7, but you can answer that however you choose. If you don't answer it, you don't get points. But if you do answer it, you get credit. And I don't care how you answer, just as long as you answer. Any questions before I turn off the recorder? Any?